Welcome to Pymol Tutorial 1, Introduction and User Interface. Pymol is a molecular modeling software used to make publication quality renders of biochemical structures. With Pymol, high-quality images, such as these, can be made. In this Pymol tutorial, you will learn how to create high-quality renders and become proficient in navigating the Pymol interface. This tutorial will cover how to install a licensed version of Pymol for PC, Mac, and Linux, how to navigate and explore the basic user interface, and we will walk through creating a visualization, including importing a PDB file, aka the rendering, how to operate the software via mouse controls and basic command line functions, and creating a simple visualization of a protein. Installation steps may vary depending on your institution. These instructions cover the process for Virginia Tech faculty, staff, and students, and may differ from your home institutions. The first step is to log into the VT Software Service Center, which I have here, using two-factor authentication. This resource is available to current Virginia Tech faculty, staff, and students only. All software available to you will be listed. Select Pymol software once you have reached the site, then the Pymol installation that corresponds to your operating system, be it Linux, Windows, or Mac. The Pymol AX software seen here is an extension used for visualization in Microsoft PowerPoint. This tutorial does not review that extension. Once you have selected your version of Pymol, you will be prompted to accept the terms and conditions. This page will look similar regardless of the version selected. The next page has two buttons to download the Pymol product key, aka the license and the Pymol installer. Both of these must be installed to run Pymol. Click Download to download the Pymol installer. Next, download the product key. Click Pymol_license.lic to download. If clicking the link takes you to a page similar to this, click the back button to go to the previous page. You should right-click and click Save Link As to download the file. Save it. And we can see we have the license and the Pymol installer downloaded. The installation I will demonstrate now will be performed for Windows 11 operating system and will differ slightly for Linux and Mac. Installation details for these systems can be found in the written instructions. Navigate to your downloads folder as I have here and open the installer. Once the installer is open, click Next, then agree to the license. On this page, keep Just Me. This will be your installation folder. Click Next. Make sure that the last box, Clear the Package Cache, is checked. You may also check the first box, which reads Create Start Menu Shortcuts. Click Install, and Pymol will install itself. Now that you have installed Pymol, launch the program. Pymol will prompt you to locate the Pymol license file with this message. Click Browse for License File. Navigate to the folder where it is, double click on it, and you should see the message, license was successfully installed. Next, we need to register file extensions. In the event that the register file extensions window does not appear, click Setting, then Register File Extensions. Click Register Recommended, and then you can close this pop-up window. Pymol is now successfully installed and ready to use. Let's cover the user interface. This is Pymol's graphical user interface. The toolbar at the top and internal GUI at the side contain a majority of the tools you will use when producing renders. At the center is the viewport, which is where your biomolecule will be displayed. The bottom of this window contains the Pymol command line. Most functions available in the GUI can also be performed through commands. This tutorial will focus mainly on the GUI and demonstrate occasional commands. Let's explore each submenu of the toolbar. The File tab is used for opening, saving, and exporting files. New Window creates a new window and allows for another instance of Pymol to run. Multiple instances of Pymol can be opened at once. The Open and Open Recent tabs allow you to select a downloaded structure file, such as a .pdb, or open a recent session .pse, respectively. GetPDB fetches a PDB model from the protein databank using the structure's unique 4-letter code. Save Session and Save Session As saves the current session as a Pymol session file, also known as .pse. Export Image As exports the current view on screen to an image file. Export Movie As exports the current movie timeline to a video file. Export Structure will export a model on screen to a file such as .pdb. And Quit closes the window. The Edit tab allows you to undo and redo actions. Note that these functions will be unavailable if Pymol is using too much system memory, such as working with a very large biomolecule. The setting Auto Copy Images, when set to on, will automatically copy images created in Pymol to your clipboard. For now, we will skip over the Build and Movie submenus, as these are used during more complicated tasks. The Display tab contains options that alter the display in the viewport. There are many options, and I will not discuss all of them, but those that you will likely use the most often are Sequence. This displays the sequence of amino acids or nucleic acids above the viewport. Sequence Mode changes what is shown on the sequence display, so you may view the sequence as atoms, residues, chains, or other. Background changes the color and type of background in the viewport. Color Space contains settings for different color palettes and allows for different aesthetic appearances, changing the color palettes approximate to making slight alterations to the color shading. Quality provides options for the quality of the visualization, ranging from best performance to best quality. Changing this setting can be useful to improving performance for older or slower laptops. Grid allows the option to display objects in a grid. Orthoscopic View toggles the orthoscopic video setting, which slightly distorts the preview window to enhance depth perception. Show Valences toggles the visibility of valences, such as double bonds and models. And Depth Q, also known as fogging, toggles fog that helps with depth perception. The Setting tab largely allows you to change the attributes of structural representations in the viewport. You can implement universal settings for each type of representation, for example cartoons, ribbons or lines, or for other visual components such as labels. Edit All accesses a pop-up window of the advanced settings available. Colors allows you to change the color of each atom type, such as making hydrogens red, and also change preset colors, such as making lime green a darker green. The functions Label to Transparency allow you to change visual settings for each of the described structural representations. Auto Zoom New Objects forces Pymol to zoom on objects as they are loaded into the viewport, and Auto Remove Hydrogens removes latent hydrogens from objects as they are loaded in. Scenes are specific views of your biomolecule at any angle or zoom. Save New Scene saves the current view in the viewport as a scene, which you can return to at any point in the future by clicking the Scenes button or the Show Scenes panel button of the Scenes submenu. Next, switches to the next scene and can be called by the page down key. Previous switches to the previous scene and can be called by the page up key. Update overwrites the current scene with the current viewport. Delete deletes the current scene. Store allows you to store scenes from F1 to F12, which are linked to the function keys on your computer keyboard. Recall toggles a scene from the list of F1 to F12. The Mouse tab contains options for the mouse controls. Selection mode allows you to change the different selection modes for selecting parts of the model in the viewport. These can also be changed by selecting from the drop-down menu in the top left corner of the screen. 3-button motions to 1-button viewing mode are different mouse control settings used depending on if you are just viewing or manipulating your biomolecule. We do not need to discuss their exact details at this point. Emulate Maestro sets the mouse to select a box area of your biomolecule, while still selecting from the parts designated by the selection mode. The Wizard tab provides special Pymol modes. Appearance allows you to quickly toggle through certain aspects of the visualization. Measurement measures the distance between two objects. Mutagenesis allows the user to mutate residues or nucleic acids by rotation, substitution, or other. Label creates labels for selected residues. And Demo allows you to play around with different demonstrations of what Pymol can do. This feature will greatly help you become more familiar with Pymol and its capabilities. Now that you have learned about the GUI, let's use these tools to create a protein visualization. The protein we will be visualizing is the green fluorescent protein from Achoria victoria, also known as the crystal jellyfish. The green fluorescent protein, GFP, is commonly used as a marker for gene expression. In this visualization, we will show off some of the key interactions which allow for its bioluminescence. The first portion to visualization is to import your model. This is done through a PDB file. The PDB file contains the data of the biomolecule structure, which was obtained by methods such as X-ray crystallography or NMR. There are several ways to import a PDB file, and I will demonstrate 4. The first method is to fetch the PDB file from the RCSB website. RCSB stands for the Research Collaboratory for Structural Bioinformatics Protein Databank and is the US branch of the Worldwide Protein Databank. To fetch the file, we will navigate to File, Get PDB. In this prompt, you will enter the 4-character identifier for your protein structure. Each structure has a unique code. The same protein can have multiple structures in the protein databank, so there may be multiple codes for any protein. Different structures will have slight variations, such as the ligands of the protein. The solvent the protein was in when it was analyzed, covalent modifications, among many others. For the green fluorescent protein, we will use the structure associated with the code 1EMA. We will enter this code in the box labeled here, leave all else blank, and our protein appears in the viewport. A different approach to the fetch feature is to perform it by the command line. Let me clear the protein on screen. For this, you would type the word fetch space and then the identifying code, so 1EMA. This will pull the PDB file directly into Pymol from the RCSB. The color change is merely an aesthetic difference due to Pymol defaults. The structure is the same as before. A third way is to download the PDB file from the RCSB website. On the RCSB website, type the biomolecule code into the search bar. The biomolecule will appear. Go to Download Files and click Biological Assembly 1 PDB-GZ. Once the file is downloaded, unzip the folder by extracting all, Now we can go back into Pymol. Click File, Open, then load the file. Similar to the previous demonstration, you can also simply drag and drop your PDB file into the Pymol application. Now that we have learned how to import structures, let's see how we can interact with the protein. I will quickly reset the protein for the first color scheme, as you likely loaded the protein just once, and this way I will be matching what you see.
Let's talk about how we can interact with our protein in the viewport. Interaction is easiest with a mouse rather than laptop trackpad. Although a trackpad can be used, it becomes trickier as there are many highly sensitive controls. In this tutorial, I will be using a mouse. Some basic controls of the mouse are left clicking and dragging about the model will rotate it in the viewport. Right clicking and then dragging the mouse forward zooms the protein out. And dragging your mouse down or towards you allows you to zoom in. Clicking using the middle button or scroller allows you to move the protein around the viewport without rotating. This can also be achieved by holding the control button on your keyboard and then left clicking. Scrolling with the mouse wheel will reveal different levels of visibility of the molecule. Scrolling towards me. Scrolling away from you will reveal more of the molecule. And these are basic ways in which you can interact with your biomolecule. Before we can get started in editing the protein, we need to set the scene. First, let's reorient our biomolecule. Now, let's set the scene. To do that, we need to initialize some settings to make the model more readable and accessible. Adjusting these settings can be done through the GUI, and I will also demonstrate how to perform these actions through the Pymol console. First, go to Display, click Background, White. To do this with the command line, type set BG underscore RGB comma white. Next, we want to remove the double bonds from our visual. To do this, go back to Display, click Show Valences. What this does is that it removes the double bonds from our target ligand. Third, we want to set the cartoon sidechain helper to on. We can do this by going to the Settings, Cartoon, and clicking Sidechain Helper. Now, from this structure, you may not have noticed any immediate differences. However, the pop-up here shows the differences between Sidechain Helper off and on. What you can notice is that the peptide backbone of the protein has been changed to be a cartoon versus with the setting off, it remains as a stick model. Last, we want to remove lone hydrogens and waters as these can interfere with interacting with protein and in general cause distractions. These red specks surrounding the protein are the water molecules. To remove hydrogens, we go to All, hover over hydrogens, and click Remove. Lone hydrogens are now removed. The command line for this is to type remove hydro or remove hydrogens. To remove the waters, perform similar actions except click remove waters. The command line for this is to type remove solvent. Alternatively, you can also type remove resin HOH. In summary, we have performed the following manipulations. We have set the background to white. This makes the protein more readable and visible, and in a publication, it also decreases the amount of ink used. We hid double bonds from showing. We hid the peptide backbone of residues that will be shown as sticks. And lastly, we removed lone hydrogens and waters using the remove function. The next important topic is hiding and showing objects. The internal GUI to the right of the viewport contains a list of all entries loaded into this Pymol session. These entries are also called objects. We can see that in this Pymol session, only the green fluorescent protein, or 1-EMA, is loaded in. Clicking 1-EMA will toggle its display. Since 1-EMA is also the only object loaded in, clicking all also toggles its display. In a session with multiple objects, clicking all will toggle the display of all objects. Now, I can add to the object list by making selections. I will add the ligand centered within the GFP as a new object. To do this, I want to zoom closer to the molecule. We can do this using our right-click and drag feature, and then left-click and rotate so we can more clearly see the ligand. We want to make sure that the residues function is selected. Then we can click the ligand in the center. In the GUI at the right, we see that a new selection has appeared titled Celle. Clicking in the empty space around the protein model will deselect this. Clicking Celle in the GUI again will reselect the previous selection. If I click on the ligand again while it is selected as the Celle object, this deselects it. The Celle object exists in the GUI still, but is no longer linked to any structures. This is seen in the command window with the line selection Celle defined with 0 atoms. I have to reselect the ligand if I want to change any aspects of it. Let's explore the different changes we can make to our objects. Next to each object entry is a series of buttons. The action, labeled A, shows adjustments that can be made to the camera in the viewport and edits to the object. A very important setting in this submenu is the rename function. To use this, click into A and then click Rename Selection. In the top left, a prompt appears. In this box, delete the current name of Celle and type in a new name. This is our ligand here, so I will call it GFP underscore ligand and hit enter. We can see that the Celle has been renamed to GFP ligand. The important function of renaming our selections is that now these are saved in the GUI at the right and can be returned to at any point in the future. For example, if I click out and then I click on this residue here, we can see that a new Celle object has appeared in the GUI panel. However, our old selection, GFP ligand, is still in the GUI. I can then click into it at any time and make edits to it as I wish. The show function, labeled as S, allows changes to the visual style of the object, such as different cartoon, ribbon, or stick representation. Different representations of the biomolecule can be shown simultaneously. For example, we are currently viewing the green fluorescent protein as a cartoon. I can choose to show the protein in the stick form. Instead of the cartoon view being replaced with a protein made entirely of sticks, we are viewing sticks and cartoon simultaneously, where the polypeptide backbone is represented by the cartoon style. We are not seeing the backbone of sticks because we set the cartoon sidechain helper to on. If we turned it off, we would then see the polypeptide backbone as sticks. Now we are seeing the polypeptide backbone as sticks on top of the cartoon representation. We never told Pymol to hide the cartoon. This shows that multiple representations or styles of an object can be displayed at once. To get rid of one of these styles, we will utilize the hide controls. Hide, labeled H, allows for the hiding of specific aspects of an object in a somewhat opposite manner to show. If I only wanted to see the stick representation of the molecule, I would go to H and select cartoon. The cartoon is now hidden and we are seeing only the sticks. If I wanted to go back to the cartoon model, I would select H and hide the sticks. I want to bring back the protein as a cartoon, so I will click S, Show As, Cartoon. You may notice that the ligand is no longer seen, and instead we have these separated loop pieces in the center of the protein. This is the ligand, but visualized as a cartoon. To bring back the stick form, we first need to click Hide the Cartoon of our ligand selection. And now we will bring it back as a stick form. One other interesting hide capability is that you can use it to hide the solvent/water molecules we had removed before. This would have been accomplished by clicking Hide and clicking Non-Bonded. We've already removed the water molecules, so this no longer has an effect, but would have removed all of the water and hydrogens. Next up is the label. This applies labels to specific aspects of an object. Let's label our ligand. Let's zoom in to the center. So if we go to our selection, click the L for label, and click residues, we add a label here for our ligand, Cro66, which is the designated name for the GFP ligand. We will later discuss how to manipulate labels, change their appearance, and other settings. The last entry for the objects entry is the color, labeled C. This applies color to the object. The color scheme for the ligand is color by elements. To change to a bright red, I will select color, and in this drop-down, click red. The ligand is now bright red. I'm not the biggest fan of this look, so I'll change it back. Color by element. This color scheme gives each element a unique color. This concludes our coverage of the object entry menus and functions. Now we will discuss important design elements. One of the most important design elements is coloring the model. Although the stick and protein are different styles, both entities are neon green, which is neither readable nor aesthetic for presentation purposes. To improve the visualization, we need to recolor both the protein and ligand. Let's color one EMA to appear light blue. Reviewing coloring, open the color submenu of the protein by going to C, navigate to blues, hover over the open submenu, and then click light blue. This sets both the protein and ligand to light blue, because the ligand is considered part of the protein structure. To make the ligand stand out, we need to change it to a different color. We have previously saved the ligand as an object, so we will just change its color in the object GUI. When picking colors for parts of a biomolecule, utilizing different aspects of color theory can be important. This is the color wheel. Colors opposite each other in the wheel are known as complementary and provides the greatest contrast. For our protein model, we want to use more contrasting colors, so we should pick colors opposite that from a light blue, which is a soft red or orange color. Let's go to colors in our ligand, and from our reds, let's look at a soft red. Deep salmon looks to be a soft red, so I'll click that. Now, I still think there's ways to improve the color scheme of this ligand. Let's go back to the color by element style we saw earlier, but this time keep the carbons this deep salmon color. Indicating all atoms of the molecule helps to show useful info, for example, potential interaction or binding sites. To do this, navigate to the C, select the first option, color by element, and then click the first option in the submenu, HNOS. Now that the protein and its ligand have been recolored for visibility and aesthetic purposes, you can render an image. First, we need to adjust the pose in the viewport. The pose will depend on what you are trying to demonstrate, or, the story you are trying to tell. In this case, we want to highlight the directionality of the beta barrel and the ligand in the internal cavity. Before we render, we need to turn off the shadows, as this could cause confusing patterns inside the beta barrel cavity in the final visualization. In the toolbar at the top, navigate to Setting, Rendering, Shadows, and click None. To render the image, go to the top right of the window to Draw/Ray. There are two ways to render an image. Draw, the fast method, will simply take a screenshot of your current viewport. Ray, which is much slower, will produce the higher quality images better suited for publication. For this visualization, we will use the Ray slow option. Before rendering, ensure that transparent background is unchecked, then click Ray. Rendering may take a few moments to complete. After rendering is complete, you will be presented with this prompt to either save your image or copy to your clipboard. Let's save the image. And save it as green fluorescent protein. Now, to save our session, we will navigate to File, Save Session As, and we will call this GFP render. This will create a Pymol.pse. Opening this file will restore all loaded objects and modify the settings for a given Pymol session. This concludes your introduction to Pymol. You have successfully learned how to install the software, navigate its user interface, and create a visualization.